particle A is dropped from a point P, which is at height h, above a horizontal plane. So there's our plane. Here's P, and we'll say A is like just below it, after it's been dropped, moving down, whatever. And we will mark on our height h, small h. Cool. So after that, what else is there? A second particle B is dropped from P and first collides with A after A has bounced in the plane and before A reaches a point again. So at some time later, what has happened here is that basically this particle has bounced upwards and has come back, and I guess it's colliding with another particle. Right. And we're not really... Okay, so what do we know? The bounce and the collision are both perfectly elastic. So what this means is when A bounces off the plane, it's perfectly elastic, which means that energy is conserved. There's no energy lost from bouncing to the ground. And that also means that, well, think about it like this. What I like to do is when we're dropping particles or whatever, you consider energy equations, right? So we know at any point you can express the energy of A. So let's do that, okay? So it's given by kinetic energy. Okay, velocity of A squared plus ma g, and I guess we'll just use HA. I mean, obviously VA is the differential of that, but this is the energy of A at any point, and we know that that's going to be equal to some constant. So what is that constant? Because total energy is conserved, so there's no energy lost. And this is how I like to think about these problems. And the constant this is going to be equal to is actually MAGH. It's the energy the particle has when you drop it, right? Because we know that when you drop it, it has no kinetic energy because it's not moving yet, and all of it is gravitational potential energy. So notice that this is the KE of the particle, and this is the GP of the particle at any point. Whatever our H and our V are, they always sum to give this constant. Okay, and no energy lost means that if we drop it, all of the GP will be converted into KE, and then after the bounce, we will still have the same amount of total energy, which means that when we solve the equation VA equals 0, we still get the same answer for our height. Right? If you solve that, we'll still get our height equal to h. What that basically means is when you drop it and it bounces, it should come back up to the same point that you released it at, which makes sense if no energy is lost, right? So what we're asked to consider is you drop A, and then it comes back up, and as it's coming back up, you've already dropped a B at some point, and they collide. Okay, and the collision we say is perfectly elastic. Again, no energy lost of the system. Now we know that the energy of B is basically analogous to this equation. Analogous, is that how you say the word? I don't really know. This is the energy equation for A. And similarly for B. It's the same thing, the exact same thing, but we're just replacing MA with MB. Okay, whatever the mass of B is, we don't really know that yet. Okay, so what's going to happen is no energy is going to be lost when they collide, but there could be energy transferred. So B could gain some energy, or A could gain some energy from B. There could be a transfer energy, but if we consider the energy of A and B, none of it's lost. What this also means is that at this collision, the coefficient of restitution is 1. So if you'd studied the coefficient of restitution from Newton's laws, this is a pretty easy one. E equals 1. So if you don't know what the coefficient of restitution is, I'll just say quickly that coefficient of restitution is just speed of approach times the coefficient of restitution is the speed of separation. Okay, in other words, we define the coefficient of restitution to be the ratio of the speed of separation, you know, over the speed of approach, the ratio of those two. So, you know, you can define it by E, and usually we say it's like V2 minus V1 over U, you know, U plus, I guess if you have two particles, and you're moving, usually they're moving at each other. So U1, U2, so this would be U1 plus U2, that would be the speed of approach. And afterwards they're moving away from each other, V1 and V2. If anyone would like me to do a video on coefficient of restitution and some problems, I will. You can pick it up pretty easily. I'll probably get around to that at some point, but it's not in the top of my priority. So if you would like to do that, just say so in the comments. Anyway, if the coefficient of restitution is 1, it means that the speed of approach is equal to the speed of separation, which is quite interesting. The coefficient of restitution can vary between 0 and 1. It means it's a measure of how the speeds change. And of course, if the collision is perfectly elastic, the speed of approach is the exact same as the speed of separation. So that's just a couple of preliminary notes. Let's just get to the meat of the question here. So, you know, before A reaches the same point, the collision's already happened. So A hasn't come back up to the point you dropped it at yet. It's coming up, but it's not there yet. B collides with it. Explain why the speeds of A and B immediately before the first collision are the same. Okay, well, if you consider what we've just said here, why would the speeds be the same? Well, what is the speed? By this equation, what would the speed be? Can we find an expression for the speed of A at any point? Well, we know that the velocity squared is basically, doesn't really matter about the direction. So that's just the magnitude of the speed squared. Let's go over here, and I'm going to rearrange that equation. Basically, this is the energy equation for A. I guess I'll just show you. You cancel the MA. And then we're going to rearrange this to get an expression for the velocity of A. So let's do that. We end up getting the velocity, velocity of A squared is equal to 2g. I think that's going to be h minus the height of A, whatever that is at. Right? Yeah, we can get that by rearranging. That's okay. So that is the velocity of A. But because B has the exact same energy equation, you also get the velocity of B to be 2g h minus hb. But notice at this particular point, HA is HB. They're at the same place when they collide. And what that means is that VA squared is equal to VB squared, which means that their speeds are the same. Obviously, we know that VA and VB are opposing each other in directions, okay, with VB here and VA here, but the speed is the same, right? The magnitude of the velocity is the same from this equation. So this is enough to say that the speeds are equal, which is good. Okay, we've done that. Okay. Notice that the equation for the energy of A still holds, and it's still, you know, this is still valid on the way back up as it is back on the way down, and that makes sense. Right, so we've done that. Okay, the masses of A and B are so we've given us ways to denote them instead of our rudimentary method. Okay, so we'll call A M, capital M, and B small m. This is an interesting condition. Usually when you're given a condition in step, you hope that you can show why that was necessary. Okay, so I'm assuming, given this condition, we want to show both particles move upwards. So that's the first thing. Show both particles move upwards. And the maximum height of B is this. And there's going to be a second collision. We also want to show that B reaches its maximum height, I guess, before the second collision. So we have to do quite a lot there. Okay, so the first thing is show that both particles move upwards. Right. Well, first of all, notice that the speed, they're allowing us to note the speed of particles before the collision is due. Right, draw a diagram is the first thing we're going to do. Always draw a diagram. These kinds of questions, because when I don't draw a diagram, I usually have one tiny thing wrong, and that's just gonna be annoying and mess my whole equation up. So we have u and u. So this is before the collision. We have b here, a here, small m, big M. After the collision, b, a, what shall we say? Let's call this v2, and let's call this v1. Okay, so we want to show that v2 and v1 are both greater than 0. What things can we do here? Okay. Well, there's two things to consider when doing these. One is conservation of momentum, and the other one is coefficient of restitution. Coefficient of restitution, I say COR. Some people say Newton's law. They just denote that by NL. So Newton's law of restitution or whatever. Right, so conservation of momentum. Let's do that. So we have taking upwards is positive. Mu minus mu equals mv1 plus mv2. Tiny m v2. Yeah, I should probably that's definitely a tiny m. It's not very clear. Sorry guys, but you know what you're gonna do. Coefficient of restitution means that the speed of approach, because it's 1, the speed of approach is equal to the speed of separation. Speed of separation is just v2 minus v1 according to our diagram. Alright, so we would like to find expressions for I guess v1 and v2. So we can just eliminate stuff here. Okay, first thing, let's eliminate v1. I guess, you know, there's a number of ways you could do this. I'm just going to multiply across by m, couple m quickly, and add them together. So I end up getting, these guys cancel out. I end up getting v2, it's going to be 3m minus m u over m plus m. And in order to get v1, what I want to do is multiply across by m, so tiny m this time, and take away. Okay, and that'll give me a similar expression. What will that be? That will be m minus 3m u over m plus m, yeah. And that's v1. Okay, and now we see why that condition was necessary over here, right? We see that we have m is greater than 3m. And of course, if m is, oh, where am I going? If m is greater than 3m, then this guy is greater than 0. And if m is greater than 3m, then this guy's trivially greater than 0, because, you know, that's at least 8m we're talking about here. And of course, u's positive, and this guy's positive, so yeah, they're both greater than 0. Alright, next bit. And we want to show that, okay, after this collision, B is going to move up. And we want B to reach a maximum height, so we're going to, how are we going to do that? Well, what is our energy equation for B? Let me write that over here. So I know that, what do I know? I think, therefore I am. Okay, so yeah, that's the mass of B. So we know that, I guess I'll just write here. And then the height of B. Remember, these sum to a constant. The constant is mgh. Okay. Now, what happened here was that this is the energy equation for B. Okay. But what actually happened was that after the collision, the speed that B should have at the point where they collided, it changed. Right, so B has a new speed. And what we wanna say is basically what is the new maximum height. So this energy equation was valid before the collision, but perhaps B now has some extra energy. You know, perhaps the system has gained some energy. Perhaps the system as B has gained some energy. Well, how do we know that? Or perhaps it's lost some energy, or perhaps the energy is the same. Well, basically, if it has gained some energy, it's going to be a change in kinetic energy, change in the speed. So we have the old KE is going to be a half u squared, but the new KE is given by a half and this would be, I think we called it V2, so V2 squared. That's our new thing there. So yeah, let's I'll write that in here. So this is what was it? I need to scroll back to see. Yeah, free m minus m. So free m minus m u all over m plus m. And we're going to square that. So that is our new kinetic energy for B. And we basically want to say there has been a change in energy of the system at that point. And that change is given by the change in kinetic energy. So let's calculate that quickly. Well, what's that going to be? It's going to be the new minus the old. It's basically a half m. Notice we can actually factor out the u squared as well. And that's going to give us, it's going to be m plus m squared. And yeah, I guess we should expand the top line out. Whoops. Plus m squared. And then we're going to take away, looks like just u squared. Because we factored out that side, that would be a 1. But I'm going to use a trick. I'm going to write 1 as the common denominator. And that expanded out in the top line is this guy here. Okay, so once I do that subtraction, what am I going to be left with inside those brackets? Well, the m squared will cancel. I'll be left with actually 8mm. Whoops, sorry, that'll take 1 away. It'll be 8m squared minus 8mm, right? And that's it. The m squared will, the tiny m squared will cancel. Be over m plus m squared. We can make that a little bit nicer by factoring out an 8 capital M, right? We can do that. Leaving us with, and because the 8 will cancel the half, it'll be 4. Looks like u squared times, well, what's that? That's m minus m over m plus m squared. Okay. Notice that's capital. I should probably find a better way of denoting between my capital M's and small m's. I mean, I don't know, every mathematician has that one thing, that one letter that looks like another letter, and it can lead to disaster at some point with the equations. But, alright. Whoa, that was pretty rough. Okay, so we have the change in kinetic energy. Now, basically what that is we're going to, we don't know if that's positive or negative, but that's definitely the change in kinetic energy. And if just by looking at it, actually, we can see that it is positive. Now would be a good time to check back to the question and see, does this look anything like what we're supposed to be given? Yeah, kinda. You know, it's getting there. There's our m minus m, u squared, m plus m squared. Oh, it looks good, right? Yeah, rubbing our hands together with glee right now. Okay, so basically, this energy is gonna go on this side of the equation, right? It's gonna affect the constant that it sums to. So this is how I would think about this problem. There's many ways to do it, you know, solve that and whatever, but you just gotta be sure you're doing it right. That this is the constant energy it sums to, and now there's a new energy. The system has a new energy, so we need to rewrite this equation considering that fact. So the new equation, you know, it's gonna be f velocity of B squared, so the sum of the KE and the GPE at any point is going to be equal to mgh plus this dude here, plus, yeah, I could denote it by star and then say plus star, I guess. That would be mathematically nice. Okay, so next is basically when B reaches the new maximum height, we have this guy going to 0. Okay. And we want to find this height. Okay, so what is that height? Well, let's just do that, right? I mean, once we write out star, we can divide across by mg. And we can get that new height, right? That's just going to be h plus this guy divided by mg. So the m will cancel. It's going to be 4m, m minus m, u squared, and then divide the bundle along by g as well. M plus m all squared g. I think that's absolutely correct. Yes. Phew. Beads of sweat running off my forehead right now. Managed to avoid any hurdles of arithmetic. Hopefully. I've seen that right. So, yeah. I mean, that's it. Right. That was the hard work. Done. Now we just need to check. I guess it's important to say that, you know, just go back and say, okay, I've done the question, right? Have I? You know, I guess the only last bit to consider here is there a second collision? When is the second collision? Well, of course it's going to be a second collision, but does B reach its maximum height definitely before the second collision? And if B is traveling faster than A at this point, then yes. Okay. And actually, well, that's kind of trivial, right? We know that because V1 and V2 have so much of the same format, we can trivially say that V2 is bigger than V1. So we know that because they're under freefall and they have the same acceleration downwards, V2 is bigger than V1, which means that A will never reach B before B reaches its maximum height. Okay. So that was step 1, 2011, question 10. Not too badly, I guess. So I hope you guys enjoyed that, and I will see you next time.